Okay, so we're going to move on to compound interest. We're trying to figure out how compound interest works and how we use it in finance. Some words we need to understand is the present value. When I refer to the present value, we're talking about the value of something today. In most cases, it's like the value of an investment. So what is the value today? Right now, that would be the present value. We could have the future value, which is the exact opposite. It's what's the value of something in the future, whether it's 1 year, 2 years, 5 years, 10 years from now. And then the concept of compound interest means that interest is compounded over a particular period of time, and in many cases it's over a longer period of time, not just 1 year, but maybe 2, 3, 4, 5 years. Sometimes even compound interest is actually applied to daily rates and even monthly rates, but for conceptual purposes, you can understand that compound interest is generally used when we're talking about greater than a year. The interest rate is just like we talked about for simple interest, the rate at which you're going to be paid or someone has to pay for borrowing money or for using money. It's the cost of money, it's the cost of capital. And the length of the investment is how long an investment will be held. Okay, so when we're comparing investments, you'll see the alternatives here. Let's compare A and B, the two investments here. One is simple interest and one is compound interest. One is over 6 years. Well, actually, both of them are over 6 years. They both are going to be paying a 5%, but you could see that the amount of interest over simple is simply going to be $3,000. But the amount of interest paid on compound interest would be $3,401. So we're thinking that we're putting $10,000 away, and when we have simple interest earning over 6 years at 5%, earning $3,000 over that period of time, you're going to have $13,000. But with compound interest, you're going to end up with more money. It'll be 6 years, 5%. Everything seems the same, except the compounding effect means you're actually going to earn $3,401. So at the end of 6 years, you will, instead of having $13,000 in that investment, you're going to have $13,401. So if we look at the investment C, we still have compound interest, but it's going to be over 6 years at 8%. The amount of interest that's going to be earned, because it's for a higher rate over the same period of time, a higher rate, you can see that significantly more interest because of the compounding effect. And that will give us $15,869. And then if you extend the time, then you really see large differences between how much money you'll have in shorter period of times relative to larger period of times. So D is compound interest, 10 years, 8%, $11,589. That means over 10 years, that $10,000 investment is going to result in $21,589. Okay, and you get another graphical representation here of compound interest over time. Two things: if the rate is higher and the time is longer, then you can see that with a $10,000 investment at 5%, you get a pretty good growth. But if it's at 8%, you have a significantly higher curve in value, and that money is going to grow significantly over a period of time. Look at over 30 years, looks like going to be close to $40,000 of at 5%, but at 8%, it's going to be closer to $100,000. Now, when we're looking at simple or compound interest computations, we can use the simple interest to find the amount, but you'll see we're going to have to be a little bit more, because it's going to be a number of computations, not just one. So as an example here, Regina Foster wants to compare a simple interest to compound interest on a $200,000 investment. Find the interest if funds earn at 6% interest for 1 year. Find the interest if the funds earn 6% interest compounded every 6 months for 1 year. Find the difference between the two, and then find the effective rate of both. Okay, so let's go ahead and pull up a spreadsheet really quick here. By the way, you can go ahead and try to solve. Maybe pause it right now and you can go ahead and try to solve. So we have it set up. The investment will be $2,000. The rate is 6%. The time is 1 year. And we're going to use I equals PRT to compute the amount of interest. So I equals PRT, P would be the principal. That's going to be $2,000. We'll just reference it, $2,000. The rate is 6%, we'll use that. and the time is 1 year. So actually, we'll just put 1 here, so for 1 year. And that would then mean that, so if we take 2,000, multiply it by 6%, and for 1 year, then one would expect to receive $120 of interest over that 1 year. That resolves A. Then it says, find the interest if the funds earn 6% compounded every 6 months for 1 year. Now, to do it every 6 months, then we're really going to have to do this computation twice. And we're going to do the first 6 months, and we're still going to use the formula I equals PRT. So 2,000 is still going to be the investment. The rate is still going to be 6%. But now time is not 1, it's 0.5. Why? Because it's 1 divided by 2 periods in 1 year, because we're doing it every 6 months. So we're going to take the time, number 1, and divide it by 2 every 6 months. That's 1 divided by 2, 1/2, okay? So 0.5. So you're saying, okay, well, look, that was the same, it was exactly half of the year 1. But now when we look at the second 6 months, the principal is going to change this way. We're going to take the $2,000 that was what we started off with, and then we're going to add to the principal the $60 that was earned in the first 6 months. So now this, in the second months, the principal is really going to be $2,060. In the second month, the principal is going to be different now. This principal is actually going to be the original principal, but we're going to add to that the interest that we earned in the first 6 months. That's going to be the compounding effect that we're learning right now. The rate is still going to be the same. The rate's still going to be the same. And the period, this is going to be for the second half, so that's going to be the same. The difference is now the compounding effect is we're adding the amount of interest we earned in the first 6 months to the principal, so that now we're going to earn interest on top of interest. Now we're going to earn interest on the 2060 rather than just the $2,000. Okay, let's go ahead and get these formatted. So we'll add the 60 plus the 6180. We earned $60 in the first 6 months. We earned $61.80. So now we're going to look at the total amount of interest earned for the year period of time. In the second example, we're actually earning $121.80 compared to the first year simple interest. All right, so we find the interest if the funds earn 6% interest compounded every 6 months. We did that. Find the difference between the two. Well, the difference is going to be 121.80 minus the 120, so $1.80. And then find the effective rate of both. We could just take a look at how it's solved here. So looks like we figured it right. We have 60 plus 61, 121.80. The difference, we did that right. Now to find the effective rate, we're going to go ahead and take the computation. If we use the effective rate computation, we're going to use how much interest did we earn in the first option, the simple interest. It's 120 over 2,000, so that's 6%. Now when we look at computing the effective rate, we're going to take what we earned in the second option with the compounding interest aspect. That was 121.80, and we're going to divide it by the principal, 2,000. If we run that number, the effective interest rate we earn is 6.1. So we earn 6% interest in this example. That's just simple interest. You get earned the 6%. We'll earn 6% compounded every 6 months. The effective rate ends up being 6.1%, and that's rounded. Let's go ahead and take a look at the next problem. The Simpsons want to buy a car in 4 years. And when they buy that car, they want to be able to put $5,000 down. Today, they invest $3,800 in investment that pays 6% interest compounded annually. Find the excess of compound interest over simple interest at the end of 4 years. Will they have enough money to meet their goal? So to review, Simpsons want to have $5,000 down 4 years from now. They put away $3,800 into an investment that pays 6% interest compounded annually. So we're going to take a look at how to compute it both in terms of simple interest and in terms of compound interest. and then we'll see if we have enough money at the end to meet their goal. Go ahead and take some time to figure that out. Okay, so we're going to compare simple interest computation to compound interest. We know that our rate, well, first of all, we know that the interest is $3,800. So we'll plug that on both sides. This is the simple interest computation on this side, and on the right side here is the compound interest. The rate is going to be the same for both. It's going to be 6%. And then the time is going to be 4 years. So we have 1, 2, 3, 4. Each one is set up 1, 2, 3, 4. Now, when we're doing this manually, it's going to be 1 year. So we'll just keep it as 1 year for that period of time we're computing the interest. So let's take a look at the computation on the simple interest side. We're going to take the 3,800. We're going to multiply that by the 6%, and we're going to multiply it for 1 year because this is the first year we're computing. It turns out to be $228 for that first year. Lo and behold, the second year is going to be identical to the first year. The principal is still going to be the same. It's still the 6%, and we're going to run that number for 4 years and understand that when we're using simple interest, the principal doesn't change. The principal remains $3,800 every year. So in the example of the simple interest, the total amount of interest earned is $912. Okay, so we have the simple interest. Now we'll go ahead and compute the interest from a compound perspective. The first year is going to be identical. We'll take the 38, multiply it by the 6%, and multiply that by the 1. However, when we compute the principal in year 2, we're going to add that interest so that we have both the principal, the original principal, plus we're going to add to that interest that's earned. And when we figure or compute the interest in the second year for 1 year, that second year interest is going to be $241.68. And then we'll just copy this down for 3, 4. So the principal, recognizing that every year the principal is adjusting because we're going to earn interest on top of the interest that's been earned in the prior periods, which becomes the definition of compound interest. We're going to sum up the total amount of interest, and the total amount of interest is 997.41. We take the difference between the simple and the compound interest. We'll take the compound, we'll subtract, we know that compound's larger, so we'll take the compound, we'll subtract the simple interest, and the total is $85.41. So compound interest resulted in higher income for that period of time for the 4 years at 6%. The difference was $85.41. Now going back to the question, will the Simpsons have enough money to pay for that down payment? They want $5,000. After year 4, the ending balance, actually we got one more to add. We're going to take the principal, we're going to add the 271, and after that interest is earned in year 4, we're going to have $4,797.41. Knowing that the Simpsons wanted to have $5,000, they're shy, they're short. They're short by how much? The difference, they need another $4,797, so $202.59. We're going to be using tables that we look up tables so that we can get the numbers we need from these tables. But those tables are worthless if we make mistakes on the front end. The compounding period is the time over which interest is calculated and added to principal. And the number of compounding periods is the number of compounding periods either in each year or in the life of the loan of the investment. We can have interest compounded annually. It could be semi-annually, it could be quarterly, monthly, or daily. If it's annually, it's one time a year. So if you look at how this has worked, interest compounded annually, that means it's compounded at the end of every year. So we have one is our number of compounding periods in a year. This is going to be important for us to know. We got to be able to take this number and figure out how to get here. If we're semi-annually, then the the interest is going to be compounded every 6 months, semi-annually, twice a year. Number of compounding periods in a year is 2. Quarterly, every 3 months it'll be compounded. The number of compounding periods in 1 year is 4. Monthly, compounded at the end of every 1 month. That's monthly, every month. And the number of compounding periods in 1 year is 12. Daily, that means it's compounded every day, every 1 day, and therefore there'll be 365 compounding periods in a year. There'll be an exception, like this year would be an exception, it's 366. We need to be able to know that when we're talking about annually, that's 1 time per year, semi-annually, that's 2 times per year, quarterly, that's 4 times per year, monthly, that's 12 times per year, and daily is 365 times a year. Now, when we're giving an interest rate per compounding period, we also have to take that interest rate, because every rate we get is going to be an annual rate. On the left column here, we see rate 8%, 6%, 4%. Those are annual rates. But what we have to understand is that may not be the rate we want to use when we're doing computations. If our rate is 8%, but it's compounded semi-annually, then what we have to remember, well, how many periods are there every year? This is an annual rate. So what are the number of compounding periods per year when we are compounding semi-annually? Well, that would be 2. Semi-annually is 2. Monthly would be 12. Quarterly would be 4. Okay. Now, the term would be how many years? Well, 4 years. That term would be given in the example. How long is this loan going to be, or this investment going to be? So we're given 4 years, 2.5 years, 5 years. This is going to be given. But before we can go any further, now we have to convert the rate and the number of periods based upon the number of compounding periods. So what I want you to remember is what you're going to do is divide and multiply, and then which one are you going to do which? You're going to divide the rate and you're going to multiply the compounding periods. If you can remember that, you can get past this pretty easy. So the interest rate is an annual rate. That annual rate needs to be converted to a rate per period. Well, it's semi-annually, so we're going to take that rate, 8%, and we're going to divide it by 2. So even though it's an annual rate of 8%, the rate per period is 4%. After we've got the new rate per period, we then need to convert the term from years to number of periods. There's 4 years in this investment, but there's 2 periods per year. So we're going to multiply 4 years times 2. So now the number of compounding periods for this investment is really 8. So even though the interest rate is 8%, because it's semi-annually, we're going to use 4% per period. And even though this loan or investment is for 4 years, because it's semi-annually, we're going to use 8 as the number of compounding periods. As an example, 6 monthly, that means there are 12 periods per year. Therefore, if the term is 2.5 years, then we've got to convert both the rate and the term to based upon the number of periods we have. How does that work? I told you. The rate is going to be divided. So 6%, that's the annual rate, divided by 12, because that's the number of compounding periods. 6% divided by 12 equals 0.5%. That's the interest rate per period. The total number of compounding periods, we're going to get 2.5 years and multiply it by 12 periods per year. 2.5 or 2.5 times 12. We get that from here. That's going to be 30. So the number of periods is 30. In the last example, it's 4% quarterly. The number of compounding periods per year is 4. The term is 5 years. So we're going to take the rate. We're going to divide it by 4 to come up with the rate per period. And then we're going to multiply it by 4. We're going to multiply the years by 4 to get the number of periods. 1%, 20. This is what we're going to use when we use the lookup tables. We'll be given this in our problems. We'll be given this, and this will be given. We have to convert the rate and the term to compounding periods. Then we can use the rate and the periods on lookup tables. In this case, find the interest rate per compounding period and the number of compound periods for each. The example A, we'll go ahead and try to solve it first. Pause it, don't look, I'll hide it. Okay, so remember, divide and multiply. Find the rate per compounding period and the number of compounding periods for each. So for A, we're going to take 5% and we're going to divide it by what? The compounding, it's semi-annually, so that means divide by 2. Even though the annual rate is 5%, the compounding rate is 2.5. Why? Because it's semi-annually and there's 2 periods per year. So we take the 5% and we divide it by 2, and that gives us 2.5. The compounding periods, the compounding periods, in this case, we'll take the number of years and we're going to multiply it by 2. Why 2? Because it's semi-annual, twice per year, 2. So the answer to A is 2.5% as the compounding rate, and the compounding periods is 6. For B, we have 6% per year, so we'll start off with 6%. The compounding periods is monthly, so we're going to divide that by 12. So the result is going to be 0.5%. The number of periods, well, it's 2. It's 2.5 years multiplied by 12. 2.5 multiplied by 12, and that gives us 30. Compounding rate divided, compounding periods, multiplication. For the last one, C, I think you got this now. It's 2% divided by what? Compounding quarterly, that's going to be 4. That gives you 0.5% on that. And the number of compounding periods, well, we're going to take 5, multiply it by 4, that's 20. Okay, before we get to the tables though, there is a formula that we can use for compound interest. It's a little bit tough. Actually, it's not that tough. It's just, it can be because you're using exponents. So especially if you're using like a hand calculator, if you have the calculator with the exponents on it, then it'll be easy. But in any event, the formula is M equals P, open parentheses, 1 plus I to the power of N, where M is the maturity value. That's going to be the future value of what we're looking at, the maturity value of an investment. P is going to be the original principal. 1 is 1, plus I is the interest rate that we're looking at. And then N is the number of compounding periods. Now that I, we got to go back to the I. The I is the interest rate, but it's not the annual interest rate. It's the compounding period interest rate, okay? So in many cases, we're going to be given the annual rate. We're going to have to convert that annual rate to a compounding period interest rate. And then in almost all cases, we're going to be given the number of years of an investment, but we're going to have to convert the number of years to the number of compounding periods, or the N. This shows how that works. If N is equal to 3, then and the result of this is 2, then to the exponent would be 2 to the power of 3 is 2 times 2 times 2. I think you guys might all know that. Here's that formula again. Now, when you finally have the maturity value, you might want to then compute what is the interest. Well, now we're going to come up with the amount of interest, we're going to take the maturity value, whatever this M equals. we're going to subtract from that what our original amount, what the principal was, and that difference is going to give us the interest. Okay, so let's take a look at this next problem. An investment managed by a Bank of America pays 7% interest per year compounded semi-annually. Given an initial deposit of $4,500, use the formula to find the compound amount after 5 years, and B, find the compound interest. Okay, so go ahead and try to solve. Let's take a look. We can use the formula M equals P, open parentheses, 1 plus I, close parentheses, to the power of N. I use the caret representation of, that means to the power of N. I can't write it small. I probably could, but it would take too much time. All we have to do is plug in the variables. In this case, P, let's go ahead and put the P here. P is equal to the principal. Looks like it's $4,500. I, now remember, I is interest, but it's interest per compounding period. So we're going to have to convert. It told us it's 7%. So we'll take the 7% and we'll convert it to whatever the compounding interest rate is. It says compounded semi-annually, so we're going to have to divide that by 2. So it's actually 3.5%. N is the number of periods, the number of compounding periods. They told us that this was for 5 years, but we're going to multiply that by 2, and we get 10 compounding periods. So I'm going to take the P. The P is 4,500. But before we do the multiplication, we have to solve for the within the inside the parentheses. So 1 plus I is 3.5%, and that's going to be to the power of 10. You could use a calculator. I use Excel to do this, but you can use the calculator. What you would have to do is first compute the parentheses. So 1 plus I, which is 1.35, because I'm sorry, 1.035 to the power. Then you're going to take that first because it's in the parentheses. Please excuse my dear Aunt Sally. Parentheses first, then exponents. So you take the 1.035 and figure that to the power of that whatever the result is, and then you're going to multiply that result to $4,500. Your answer to this, the maturity value, is equal to $6,347.69. The next part is to figure out how much interest there was. Well, we started off with the principal of $4,500, so we have the maturity value, and as we learned earlier, the difference is what we're going to figure out to be. The difference is going to be what we earned for the period. So the interest earned is $63,447.69 minus the $4,500. So in this investment, we've actually earned $1,847.69, which should be $1,847.69. Yep, that's what they have here. In the textbook, they actually show you how to use the calculator. So if you're struggling with using the calculator, make sure you refer to the textbook. I mentioned earlier that we're going to be using tables to solve this. We went ahead and figured out a formula first, but now we're looking at tables, and the tables are going to be easier than the formulas, obviously, because that exponent really makes it a little bit more complicated. But the one thing we can't miss on is the number of periods isn't the number of years. The number of years has to be converted to the number of compounding periods. That's the N, the number of periods. And then the I has to be computed from the annual rate to the compounding period rate. Okay? So once we have those numbers, we then have a table we can look up. This is the compound interest table. See that? I'm sure we'll come back to it, so let's go ahead and move over to the next. In each case, find the interest earned on a $2,000 investment. Okay, so, and I'm sure they're going to want us. So we set up our table. We have we set up our table here. We have 4 different options, 4 different terms, 4 different rates. All of them with the same amount of deposit, or what you can think of as the principal, the original invested amount. In the first example, A, it's 3 years, it's compounded annually. So that's pretty easy. Compounded annually is going to be three compounding periods. I, we're given a rate of 4% for A, 4%, but that has to be converted. Well, actually that makes it real easy because it's annual. So that's going to be 4%. Perfect. Now that we have the N and now that we have the I, we can use the lookup tables in the periods. The period is 3, the I is 4%. So period 3 and 4%, we'll look for the intersection. 3 and 4%, it's 1.12486. 12486. That's what we're going to refer to as a factor. The factor, what we're going to use to compute all this is 1.2486. We'll take the deposit, we'll multiply it by the factor at the end of 3 periods at 4%, at a 4% per period. The factor will do a lookup for 3 years at 4%, 1.12486. 1.12486. We'll take the deposit, the principal, multiplied by the factor, 2249.72. And then the interest that we earn for that period is going to be the maturity value minus the original deposit. So the amount of interest we earned is $249.72. In part B, we're looking at 5 years. So we're going to take 5 years and 5 years, and the compound period is semi-annually. So the number of periods, that's going to be a multiplication. So that's times 2. Number of periods, multiplication. So they're really looking at 10 periods. The interest rate is 6%, and that's going to be divided by 2. The interest rate for per compounding period is 3%. 10, number of periods is 10, the rate is 3%. So 10 and 3. Let's go look it up. Look it on the table. 10, 3. 10 is number of periods and the rate is 3%. Okay, 3%. 1.34392. 1.34392. 1.34392. There it is. All right. The maturity value, we're going to take the original deposit, multiply it by the factor. Boom. Now we have the maturity value. A little bit easier than actually using that formula that we learned earlier. And if we want to know how much interest we've earned, we simply take the difference, $687.84. For C, 6 years, compounded quarterly, 6 times 4, it's 24 periods. The I, 8%, divided by 4, compounded quarterly, is 2%. The factor, 24.2. We'll go to the table, 24.2. Where's 2 at? Right here. And 24. 1.60844. We'll take the deposit, multiply it by 1.60844. Maturity value is $3,216.88. The amount of interest is $1,216. That is $3,216.88 minus the $2,000, $1,216.88. And the final one, 2 years compounded monthly, 2 years compounded monthly. So 2 years, 2 times 12 to get the number of compounding periods, that's 24. And the rate is 6%. And that's going to be divided by 12, which is going to really be 0.5%. All right, 24 and 0.5, or 1/2. 24 and 1/2. Let's look for 24 periods at 0.5%. 0.5% for 24 periods, 1.1276, 1.2716. We're going to take the $2,000, multiply it by the 1.12716. We'll come up with the maturity value of 2254.32, and then we'll find the difference between the maturity value and the original deposit of $2,000. So the amount of interest earned was $254.32. Now you can see the textbook goes on to explain how you could actually do the computations using a financial calculator. And you'll have to learn the term present value. That's what the current value, that's going to be like the deposited amount, the investment, the present value. Those are all the same thing in this context. Future value would be like the maturity value, how much you can have when this all ends. That's the future value. I is the interest rate that you would use per compounding period. So you're still going to have to do that conversion that we're learning. You can't just use the rates that are given to you. You got to convert them. And then N is the symbol that represents the number of compounding periods. Every calculator is a little bit different, but they'll give you kind of a feel for how to use your financial calculator if you're using that, or there's some online tools as well that you can use. All right, so let's take a look at the next problem. John Smith sold his truck for $15,000, which he deposited in a retirement account that pays interest compounded semi-annually. How much will he have after 15 years if the funds grow at 6%, 8%, and 10%? So the first thing we're going to have to do is figure out what the rates are for each scenario. So let's go with A, B, and C. He sold his truck for $15,000 and he deposited that into a retirement account. So let's go ahead. The deposit amount for all examples here, $15,000. And the term, the number of periods is 15 years. But before we go with 15 on this, that's 15 years. We have to convert that to the number of compounding periods. It pays compounded interest semi-annually. So that's going to be plus 15 times 2. So in all cases, we're looking at 30 periods, 15 years, 30 periods. Here's where we're going to get differences. The rate, 6% divided by 2. So it's actually 3% under scenario A, 8% divided by 2 under scenario B, and 10% divided by 2 under scenario C. Now we use our lookup tables to come up with the factors. 30 at 3%, 30 at 3%. 3% is here. Let's go down to 30. 30 is the last one. 2.4276. I'm sorry, 2.42726. 42726. 2.42726. The factor we're going to use for 30 years at 4%, 3.24340. And the factor we're going to use for 30 years at 5%, 4.32194. We got everything we need now. We're going to take the original deposit, multiply it by the factor. We'll do that for B and C. And just for kicks, I don't even know if we were supposed to do that, but we can figure out how much interest it is between the three options. We're taking the maturity value and we're subtracting the original deposit. So the problem wanted us to use both the tables and use the formula to do the computations. We used the tables, or I just used the tables, and I think we did on 36,408.90, 36,408.90, 48,651, 48,651, and 64,829. So this is what we came up using the tables. If you use the formula, you would take the same 30, it's 0.03 or 3% and 30 years, and you'd plug them into that formula that we learned previously. What's that formula? P, open parentheses, 1 plus I to the power of n. Using this formula, you'll find that there'll be small differences between the two answers. The formula is going to be a little bit more precise, but you're going to have to do some rounding and using the calculators to make that all work.